This session we have like very root dedicated, and the first talk it will be probably the hottest development of the last two releases is TDataFrame that offers high-level interface for the data that starts in root. So I will.
Right. Thank you, Oksana. My name is Enrico Guiraud. I'm a doctoral student in the root team. My PhD project is more towards machine learning, unsupervised machine learning algorithms of interest in high energy physics. Since the start of last year, started a little side project that then became official root development. Other people joined, and now it's been almost 1 year that we've been developing this TDataFrame interface for root data analysis, and this is what I'm going to present today. Obligatory motivation slide. Root's mission is to get physicists from collision to publication quickly and correctly, right? This is a stated goal of the root team, and in particular when it comes to data analysis. The more towards the end of the life of the data points that are taken, right, from collision to reconstruction up to the laptop of the high energy physicist. What this means, and what this goal translates to, is we need to strive for a simple programming model. We need to allow users to effectively write efficient code. And given that everybody today has at least 4 logical, if not 8 logical cores at their disposal on their laptops, we need to allow to easily express parallelism. Not everybody is a parallel computation expert, but everybody has that power on their laptops at their disposal. On the other hand, this is the current interfaces that this is the current interface that root has a standard for reading and working on root data. It's the teacher reader interface. I guess most of you are familiar with it. One declares a teacher reader object, then declares readers for different branches of the tree, or meaning columns of your columnar data storage, X, Y, and Z. And then you write the event loop, right? While there are data points, if the data point passes if the event passes my selection, then I fill a histogram with it. Okay, simplest analysis ever, but it's a good exemplar of what people want to do. Advantage of this approach is that you write your own event loop. You have full control over what happens with your data once they have been read from disk. But it does require some boilerplate, and users have to implement common tasks like more complicated fillings of histograms, or even parallelization. If they want to do this in parallel, it's a bit awkward. People, I guess, use T-selectors, or more people probably just spawn more Python processes running on different files. What we propose instead is something like this. This is the new thing. This is TDataFrame. It's a declarative approach, just like Pandas offers, or Spark. Spark DataFrame. It's really simple, right? You just declare your DataFrame object, specify what's the data that you want the DataFrame to act on, and then you write your analysis, or a functional chain, or as we'll see later, a functional graph, right? So you say, I want to filter according to this function, is good entry, apply to columns X, Y, and Z, and then I want a histogram out. And that's what you get, a histogram. So you have full control, but not over the event loop, but over the analysis, over what happens in at the analysis level. No boilerplate, common tasks are already implemented. And what about parallelization? Well, it's just one line more. If you enable implicit multi-threading by calling the appropriate root method, TDataFrame will spawn several Intel TBB tasks. Each one will take a cluster of entries. So we do event-based parallelism, right? Tasks work on batches of entries, and then we put together the results. Under the hood, the user doesn't have to change anything else other than adding this little line over here. So we want a simple and powerful programming model. This is really what we have been strived for. And the interesting feature of declarative interface is that they provide high-level features, while they allow the developers, us, to offer transparent optimizations without the users having to worry about multi-thread parallelization, lazy evaluation, caching, and more. This is available since root v6.10 in the root column experimental namespace. Many new features have been added in v6.12, and we plan to get out of the experimental namespace with the next official release. We still want a bit of user feedback first, but the code is stable, is very well tested. We have a plethora of Google tests. Mainly we stay in the experimental namespace to be sure that if we want to tweak the interfaces a little bit more, make them a little bit nicer for users, we still have this freedom up until the next release. So, a bit more about TDataFrame. This is how your analysis looks. This is one of the ways that your analysis can look. You declare your TDataFrame, specify the name of the tree, the name of the file. In the next line, you specify one of your functional chains. You say, look, I want to filter for theta greater than 0. Note that this is a string. Then we just-in-time compile into a lambda that does the same job. It just checks whether your variable theta, your branch theta, is greater than 0 or not. And then I want a histogram of a variable pt. You can do the same on a different line, different functional chain. This time we define a new variable r2 with this expression. It's just right the square sum of x and y, and then we want to plot r2. So this I'm plotting two different histograms, but actually this is going to be just one event loop, because what actually happens when you write these two lines is that TDataFrame builds the computation graph, right, which looks like here in the figure. Computation graph for us consists of a series of transformations in orange here, so filters or defines. There are another couple of things that you can do to transform your data set. And then at the end of your graph, the leaf nodes, they produce the results, right? And what they actually return are not actual histograms, but let's say proxies to histograms or promises to histograms. And upon the first access to one of these TDataFrame results, the first time that a user tries to actually draw the histogram or check how many entries it has, then we evaluate the full graph. And in one event loop, we fill all the registered, all the pending results. Okay. Not just C++, but absolutely pure C++ is supported. It doesn't have to be a string, what you use in a filter or in a define. You can pass a lambda, a functor class, or any other callable object, anything that has an operator bracket that we can call. And you can also pass the types of your branches as template parameters. Let's see this in a bit more detail. So here I have a data frame, specify a filter, to which I pass a lambda that just checks whether t is greater than 0. And I want to apply this lambda to branch th, right? And then the action that I do is this snapshot action here. What snapshot does is that it writes to file. It's a save to file action, okay? And the arguments it takes are the type of the branches that you want to save to file in a new T3. Okay, this produces a new T3. So in this case, my branch is of type vector float. T is the name of the new tree. F.root is the name of the new file. And pt_x is the name of this branch. Of course, I can specify multiple branches and multiple templates. Multiple template parameters. And I save to disk more than one column. So this is a very easy way to scheme your data set, right, and save the scheme version. If this is too much typing, you can always rely on jitting. You lose a little bit of performance. There are going to be virtual calls that are not there if you do not rely on jitting, right? If you explicitly specify all the types, so the compiler already has them at compile time. If you don't specify the types of your branches, if you don't pass template parameters to snapshot, if you don't give us a lambda but a string, then we read those types from the file, right? We know at runtime what type each branch is, and we JIT everything. We also offer a Python interface, which looks very, very similar to the C++ with JITting interface. You can leave out the semicolon because it's not required in Python, but the rest is exactly the same. What are the things that you can do with TDataFrame? As for transformations, you can define new columns as complicated as you want. Define slot and define slot entry are two other ways to define new variables in which the user also has as an available variable, and as if it was a column of the tree, the entry number and the slot number, which specifies which thread in a parallel execution is processing this particular entry. This is just a helper to help users write thread-safe code more easily. You can filter, and you can just run on a range of entries. So if you're doing quick prototyping, you don't want to run over your 10 gigabytes of data, you just specify range 10,000, and you just run over the first 10,000 entries. As for actions, you can count the entries that pass certain filters, or you can take the minimum of a quantity, maximum, mean, sum. You can sum the quantity. You can produce histograms, profiles, 1, 2, 3D. You can fill a generic object because the histo actions always return a th1d, but maybe you want a th1f, so you can pass it to our generic fill action. And then, in more and more generic actions are reduce. It's a generic reduce operation in which you pass your reduce lambda. This is the functional programming style reduce. Just a for each. So for each event, execute this lambda or this function or this functor class, whatever. Give me all the entries in a vector or a snapshot. So save to a file. Coming soon, it's an accumulate, like it's a more generic reduce, something that returns a scatter plot, a t-graph, and something that returns a standard deviation or a variance. Putting everything together, this is the 4 lines that produce a scheme, thin, T3, and a histogram running the same event loop on a CSV file with multiple threads. Okay, it's just 4 lines. You enable implicit MT, implicit multi-threading in root. Then you construct a TDataFrame with this factory method that actually constructs it so that it reads from a CSV file rather than a root file. We'll see how this works later. But we also read CSV files. Then you book the creation of a histogram of variable z, and then you ask for a snapshot. So this is meant to show that the programming model is simple, readable, but nevertheless powerful. So what about performance and scaling? This is all cool, but is my analysis going to actually run faster? The answer is yes. Jakob Blomer presented a quantitative review of data formats for high energy physics at ACAD 2017. And as part of this review of data formats, there was also a review of the ways one can read the root data format. I just extracted the plot from his presentation, and that is here. So we have on the left, the blue bars are performance on an uncompressed root file, and in red on the right, it's performance in reading a zlib compressed root data. The data set, the specific data set is the one available, made available by LHCb through LHCb Open Data. Jakob calls it a fruit fly data set in that it's not the most realistic example ever, but it's representative of what it's usually in an analyst's data sets. So we can see that set branch address, so a pure low-level T3 reading has quite a bit of advantage. Higher is better because it's y-axis events per second processed. So a set branch address has quite a bit of an advantage with respect to a T3 reader. This overhead is actually not intentional and is being worked on. TDataFrame is based on T3 reader, so it has same performance with a slightly more, a little bit of overhead. But as soon as you go multi-threaded, you get back everything that you lost and more. And given how easy it is to fully exploit all your cores, this plot kind of shows that TDataFrame is a viable alternative to other ways to read root data, and you might want to try it out. This is for performance. When it comes to scaling, we took Xavier Valsplat, another doctoral student in the root team, and we asked him to rewrite a full-blown analysis code written in root 5 by René Brun, so creator of root. These two plots show the actual wall clock times executing on a many-core architecture, KNL machine of these analyses, and the speed up. So the lesson here is that TDataFrame has a very little overhead with respect to an ad hoc code that was written specifically for that application, with many tricks to parallelize everything, even in root 5. Some locks were taken out, some locks were put in. TDataFrame is more generic and performs quite well at the level of the original application. And we scale up to 120 cores. We actually ran over 250, which is the full capacity of this KNL machine. And the scaling is not ideal, of course, but we still get speed ups as the number of cores go up. And performance optimization of the TDataFrame is always in progress. It's being this new code, we will work on that a bit more during the next year. A few more features. How much time do I have left? 7 minutes? Yeah. Okay, so I'll go pretty quick. So this is the mechanism that allows us to read from CSVs and other data formats. So TDataFrame does not read CSVs directly. There is another class that is part of the TDataFrame framework, which is TDataSource. Users can implement their own TDataSource that reads a certain data format. It has to be a columnar data format. But given a TDataSource implementation for that specific data format, then TDataFrame can use it. It queries this TDataSource to actually read the data. So this puts a layer of indirection between TDataFrame and the actual data format, and makes us capable of reading pretty much any columnar data format. We currently support CSV through this mechanism, but we also implemented proof of concept data sources for the root data format to show that we could deal with that kind of complexity with our data source API, and LHCB's binary MDF format. So we can even read binary formats. One can also specify callbacks to be executed every n entries in the event loop. This is quite useful if you want to inspect partial results of your analysis without waiting for the analysis to actually finish, right? If your analysis runs for 1 hour, you probably want to check that the histogram is being filled sensibly, maybe every 5 minutes or so. And this is how you do it. You book a histogram. You call this TDataFrame.histo1d of X. You book a histogram, and then we go to the last line on the slide. We say on this histogram, on partial result, every 100 entries, I want to execute this callback. I want to execute this callable. This callable in this case is draw H, and all it does is plotting the histogram on a canvas, and this gets you the histogram updating in real time while the analysis runs. This also works in multi-threading, by the way. Finally, last pretty cool thing is that TDataFrame does not only read data, you can also use it to create data from thin air. In this case, the interface is the following. You say, TDataFrame, you are a TDataFrame with 100 entries that for now are empty. And then you can define quantities, right? You can define your columns, passing in lambdas or whatever callable. You can say, look, my X is just a random number, and I define Y as X plus some noise. Okay, and if I then call snapshot, I'm saving to tree this data set that wasn't there before. This works in parallel, event-based parallelism again. It is the easiest way to create new T-trees in root, at least in my opinion. People might disagree, but it's just 4 lines, and it does something quite sophisticated. And as a proof of concept, we have been using this to write events on a T-tree generated by PCI8, so in parallel. So we have 1 PCI instance per thread producing events, right? And we just define that as that PCI produced event as a variable, and then we snapshot it. As long as we have dictionaries, that works. But cut flow reports are easy. When you have filters to which you give a name, you can just ask the TDataFrame for a cut flow report, and it prints out what each filter, how many entries each filter has seen, and how many pass the filter if you need to fine-tune your cuts. So in summary, Root provides a modern, declarative, type-safe, parallelized interface for data analysis in the form of TDataFrame. It is performant, it scales to many core architectures, and aims to offer everything that high-energy physicists need for their analysis. Right? This is, we would really like to see this as the go-to way to analyze root data formats, root data sets, and data sets in high-energy physics in general. You can use it from root macros, from compiled code, or even from a Python notebook. Actually, if you check out our tutorials by looking for them on the root website, they're all executable in a Swan notebook. And we have them all in Python as well as in C++. For the future, we are currently thinking about doing R&D in the direction of distributed execution, so running on multiple nodes, but still letting users write their analysis with this simple high-level interface. We have been asked multiple times for more syntactic sugar for common operations on arrays. We have something in this direction, so if you have a column that is an array of doubles, and you fill a histogram with it through TDataFrame, we know that that what you actually want is to fill the histogram with each one of the elements of the array. So these kind of things are already done under the hood, but we want to offer more and more, really syntactic sugar to not have users write loops over arrays, which is something that's really common and possibly error-prone. We want a fast path for reading files containing very simple data. Jim, for example, showed that with uproot that this is possible when root files only contain doubles or arrays of doubles. One doesn't need to load the fully capable root I/O. One can do things more quickly. And Brian has been working on integrating bulk I/O in root, which is something we want to take advantage of to do exactly this, to go exactly in this direction. The cool thing is that users don't have to change anything. right? If new optimizations come along in root and become available, we can just adopt them and offer them to users in the next root release transparently. So their code just runs faster, but they still use the same interface as before. And finally, we haven't really we still have to dive into low-level performance optimization, checking where the bottlenecks really are. Of course, we fix all the obvious things that we could see, but stuff like cache locality and more opportunities for parallelization. This is still to be investigated, and it's a work in progress. And that is all on my part.
Thanks. Any questions?
Yes, one question. Is this so geared for raw, wise, and tuples?
Sorry, I couldn't hear very well. Could you?
I am asking if you can use this only for raw, wise, and tuples.
What raw, wise, and tuples? I'm not sure what you mean. So the original aim was the root data format. Now through TData source we support potentially any columnar data format. In practice, we just added CSVs for now. So as long as it's columnar and it's fine to process one event at a time, TDataFrame is probably a good choice.
So if I understand correctly, it's like a sort table, like to use, for example, in R in some type of languages. If I have events with one event with 5 tracks, one event with 10 tracks, and so on, then you can't use this for this type of data.
I'm not sure what you mean with one event with n threads.
So one event with 5, for example, tracks, one event with 10 tracks. This is the column wise and tuple.
So the
yeah, that works without a problem. Anything that root IO can do, TDataFrame can do. So yeah, if you have a variable size column, that's no problem. It's not limited to fixed size and tuples.
Absolutely.
So this is Mike. What is the bottleneck? That is it the I/O or is it the execution of the code over the data? Do you understand what limits performance?
Definitely when you're reading from disk and you're not generating data on the fly, bottleneck is I/O. And that's why we are really looking forward to bulk I/O and other ways to read root data faster, because that's definitely the limiting factor. When you scale to many cores, the raw I/O throughput of your disk might also become a bottleneck, right? Because you cannot, if 250 threads are waiting for the disk to give them the data, that's probably suboptimal. And there, actually, we might want to adopt a different parallelization scheme to just having each one of the threads hammering the disk. But yeah, definitely I/O. That's the main thing. In second approximation, that maybe we might be memory bound for certain specific applications in terms of cache misses and so on. But this is really a second approximation.
And Mike, to be clear, when we say I/O here, we mean the root I/O subsystem, and not necessarily the I/O subsystem of the host.
Yeah,
right?
the whole thing.
Oh, I don't know. Remember, Brian, I'm stupid. I don't know any of these things. You have to tell me.
Yeah. So the root I/O subsystem can has various internal overheads, internal locking, or decompression, and that's going to, in terms of the host, if you're looking outside the process, it will look like it's CPU bound, but there's really all the CPUs, everything's tied up in the root I/O subsystem. It's not necessarily the speed of your SSD or your disk that's the limit.
Yes. So when I say first approximation IO, definitely IO bound, I mean all the steps of root IO. So it's first reading from disk, second unzipping, and third deserializing the unzipped buffers, right? So getting the raw bits and making them into C++ structs. So all this takes time, and it's the thing that
So do you understand which of those three elements might, if I've got an n tuple with 237 columns.
Yes.
A perfectly reasonable number, unfortunately.
Yes.
With a couple million events.
Mm-hmm.
Which of those three elements is likely to be the bottleneck? Is it really the physical access to the disk? Is it the decompression? Is it something else?
I'd say, from what I saw from our first profiles, it's probably decompression. But it also depends on your disk. It depends how many threads you're hammering your disk with. Because if you have, as I said, 250 threads reading 250 different events each, right? Each one is reading one different event. Then the disk, then raw disk I/O might start becoming the bottleneck because the disk just cannot keep up with all these requests. So it's not, there's not one answer, but R&D is going strong there. Brian knows root I/O is always under optimization.
So, shoot, Oksana knows too, but yeah, and Mike, the answer differs depending on hard drive or SSDs, and it also depends a lot on what the types, how complex the types are in your n tuples.
So if you spread the data out over 8 disks instead of a single disk, would that offer the possibility of speeding things up? Because I know when we do the Globus transfers, with 8 different, I don't know what you would call them, running in parallel, that gets a lot more speed.
Potentially, yes. I don't know in practice whether the operating system allows you to pin a certain thread from reading a certain disk. I really have no idea.
So Mike, in that case, you're best off taking 8 separate input files.
Right.
So the way root I/O is created, you gain very little by spreading one file over multiple disks because the internal structures are not going to align well with any scheme for splitting a file up over disks. When you do transfers through grid FTP, the multiple streams work around a very specific TCP implementation issue that doesn't really apply here, speed of light type stuff. But so your best bets to speed things up would be to analyze more files in parallel. And
right. Okay. I think that's what I'm asking. I'm just thinking about how the experiments could organize their data, right, to enable better clock speed.
That's highly dependent on the experiment framework, I'm afraid, and not directly related to how TDataFrame does things. Because, for example, was talking today to people from Alice, and they have a very complex data format until, at least until run 3. They will have a very complicated data format to the point that deserialization for them is a bottleneck. So really just raw bytes from memory and converting them to C++ structs in a sensible way. So for that, because they have T lists of T lists, so that's a bottleneck for them. I was at the LXCB workshop 2 weeks ago, and in their case, they're making everything possible to quickly move the data from one step of their high-level trigger data acquisition queue to the next. So for them, it's data transport besides other things. So really depends. But the good news is that TDataFrame is agnostic to how you actually read the data under the hood, and it offers this simple, high-level declarative syntax for data analysis that we want to make as powerful as anything else that you can do with root. If we're not already there, actually, I'm not aware of a use case that we don't cover. And at the same time, you take advantage of any specific reading technology that you might have under the hood, right? So if it's a CSV file, you can forget about all we said about the bottlenecks of root I/O. What you want is probably memory mapping the whole thing and then reading pieces of the file from memory. So bottlenecks there will be completely different.
I'll be a little bit of luck. I can take one of my existing analysis codes and rewrite it to TDataFrame and give you some feedback.
I would love that. We would love that. If there is one thing that we're really missing is more and more user feedback, knowing what we did right and what we can improve on.
Yeah, and I'd second that.
Have you organized, I mean, are you reaching out to the analysts in different experiments with explicit, with workshops that give examples of what's been done inside that experiment and sort of
yes,
walk
absolutely.
people through conversion of existing codes into TDataFrame? Because it makes complete sense to you, but it looks a little bit opaque to me.
Yeah,
absolutely.
The
Structure, the grammar are not obvious for someone who's used to the, the make class version.
Yeah, there are people at Bell too have adopted TDataFrame with its Python interface for the data analysis. There is Stefan Bunch that is pushing for it, so they're giving us valuable feedback. I know of a couple of people from CMS that theoretical physicists that now run on simulated data with TDataFrame. We were in contact with that. Absolutely, I was at the LXCB workshop to present TDataFrame and get feedback from them. Absolutely.
Was that the software and computing workshop?
Yes.
Okay. So this year there may have been more analysts there, but typically that appeals to the core computing community. So you might want to just do tutorials at CERN.
Yeah, that's.
To get 20 people in the room, and then have them convert some existing analysis code to TDataFrame just to see how it works.
Sounds good.
So I will propose, in case you can, start some mailing thread if you're still interested and you have more questions. Yeah, because we are running really out of the time. What do you think?
Yeah. Absolutely. There.
Thanks. And okay. So next will be me, and I wanted to propose you to look into our progress report on root modularization. So basically, I have two parts. One is on updates on by itself proposal that we were working on last month. And here, basically, I just wanted to say that it was hard to define some, you know, the motivation, the basic entities, what is package, what is model. So we'll just go past, and there is the links, and you can click, and you can go comment, and we will be super happy if you will share your ideas or your thoughts. So what is the goal, what we think, what could be useful, the root modularization? It's not C++ models, as we heard before. So basically, the important part is that root is very monolithic software package, and we can do boundaries and relationship a bit more explicit.
Are you sharing your desktop?
No.
Yeah, I see the slides, Mike.
You didn't see?
No, I think it's a problem.
Who knows?
They show up for me, or at least slides.
Yeah, I see it fine as well. No problem.
Okay.
My problem then.
Sorry. So then we can really define and implement the minimal root, and this thing, which we will call minimal root, it should help root users to interact with wider data science ecosystem. Then it's probably also a nice thing because it will help root users to socialize and reuse projects on the top of root. And the coolest part is probably that we can go together and try to, you know, define some community package format for community and go together with a similar direction. The concept, just super fast, what we define as a model here, it's just a set of independent classes, and which is implementing some coherent functionality, and they have well-defined APIs, and they actually, models also could contain data files that are not necessarily class implementation. Then library is actually a model, a set of the models, and package in our definition is something like a distinct self-describing resource file with a URL that could provide one of the more models. We expect to have a package database or something similar, which will record all package available on current root installation and already installed. And of course, the main goal is to go and try to define the package manager, which will be a main actor for us, which will locate, install packages from references and along with their transitive dependencies. So on previous presentation, there was a lot of questions because there is a bit confusing package manager. If first thing that you see, it's usually operation system package manager. Here we interesting maybe in dependency resolution or something for operation system package manager, but for us it's so I found the definition of the existing definition of possible package manager, and I think root modularization, I will not go through the slide, it's something more than a language package manager and project application dependency manager, which will unite together functionality as a read. So if to go through the, you go to GitHub and you check what is existing open source package managers, the most start, and you see that it is most of them with wide support community. We are not interested in web. We didn't say anything. It's Alcatraz, Homebrew, but it is pure operation system package manager, missing one on Mac, and Swift package manager, which is Swift is a language actually. And this was our inspiration because Swift package manager, kind of nicely aligned with the root needs. And then it's also providing a nice interoperability with C, C++ based languages through the use of Clang, so we use C++ model system. If you go to the link, you can find in the documentation, there was like the first approaches of Swift community to define the package manager, and we were like really inspired by their text. So ideas, what was interested, that root is kind of compiler by itself, that we have PCH and dictionaries, and for better modularization, we need to achieve PCH separability, because you cannot load more than one PCH. So in this case, it could be really done via C++ models by generating C++ model for each new root component to be plugged in. And this is also very nicely aligned with it's a logical continuation of work done on C++ models for root and then integration for CMS software stack. So there is, I don't know, I think I was mentioning before, or Vasil was mentioning before, there is a root evolution repository in root, which is supposed to track kind of new proposals and something that, yeah, that will make root evolve in better root. So here I created one of PRs with our modularization proposal, and hopefully we can, if you want, you can look there. So updates on prototype, the most interesting part, what we have now. So we have a base option, this, you know, root part, which supposed to help us to provide modularization process, and it is available on branch Shadura base, but hopefully I will do some PRs to it to integrate it. And big thanks to Rafael for helping with initial implementation. It was a cool hacking together. So there is a lot of CMake improvements, which is so basically introducing new macros, which is allowing to build a root model on the top of our root base. I will go a bit later, and I will explain what is root base actually. Better separation of models. So while going through base and trying to plug our first model, we found that there is a lot of cross-TU dependencies that it should be fixed, which is the resulting linking errors. There is also header dependencies, which you cannot see them through linking errors, but actually when you start to build the boundaries, then you can notice that there is something going wrong. And we did some cleanup of unneeded legacy dependencies in root binaries, and also like some legacy code cleanup. So basically, this process is actually kind of interesting from the point of view of cleaning up existing root. Oh my God, implementation. So about base, what is base for us? So in root was existing such option like a root minimal, and I draw it here in blue. It is actually all libraries models which were proposed by minimal, which is not really minimal root. So we decided that the most the core part of root is actually really core, Rio and Clink in this case, and here you see a list of directories that are used for the base. The pros of base, it's basically, it separates the fundamental part of root, which takes the longest fraction of time while you're building root. As I told, it really defines, you can start to see the pure separation between models and core by itself. It helps refactoring includes, and all changes they're totally transferred, so they're not hurting nobody. And then, for example, there was such an idea that base could be easily released as a Docker container and help to provide Travis CI support for new root models or external project testing, which is based on root. So just a tiny example with which we were playing. We took XML.io because XML.io is from Rio, which was not included in Rio while compiling. So basically the only dependencies that it has is base by itself. And we use like a YAML manifest to try to, with the help of Bash and Python script, to prototype the expected behavior in the tool, like query build models or build missing dependencies in this case. And so, like, I know it's a screenshot and probably not visible, but you can see here is like we're building root base, and then on the top of it, we were able to build XML.io model, and then just include in test. We also included like tests of XML.io basic functionality to be sure that the process was successful. And so the plan of the work, which I want like now to speed up a lot, is to try to go step by step and to provide something like minimal root with a base properly when you will be able to test it, to work on the prototype tool possibilities, to list all models, to do extra queries on root dependencies, define the package format, try to go through all list of the models and see what we will get, how if it will work 100% with all available root models. Then try to see the next step will be to improve our prototype and try to go on a lazy install based on some missing package, and also check if we can do some external package resolution. And the third one is just to finalize and see for various packages for in-source and external modularization in case. And yeah, so thank you. It's super fast, and I hope in a few months you will get a full update.
Thank you, Oksana. Are there any questions? Remote?
So what do you what's the target user of such a system? Someone that uses root on a laptop, or people that actually deploy root?
I think it's it should go both directions basically. So first one is to probably improve the possibility for. Okay, first thing it's improve absolutely the root quality code. The second thing, in terms of separability of our libraries, and if somebody accidentally left there, I don't know, one header or something, it just clean everything. The second thing is that for developers, it would be useful when you don't want to pull everything, but in some moments you would like to test some extra functionality or whatever. Like for example, you will work on TDataFrame, and you will not pull every TMVA. You will not need it. Mm-hmm. But in case if you will need, you will just go and momentarily pull it and build and or update also. And the third thing is probably also it will give possibility to create more flexible configuration for everybody. Not CMake dot and or CMake dot go ahead, but to have more custom settings for your own build.
Okay.
Yeah, I mean, I see this, kind of in order it's useful for developers, both internally to root and those who are trying to build things onto root without, it gives maybe a better avenue to not have everything upstream, but be able to easily add to the ecosystem. I see a lot of value for analysts in order being able to share and quickly bolt things onto their roots installs if they want. But as far as experiments, CMS or LHCb, they have enough, to some extent, they have enough software engineers that are going to blow through any obstacles as is. So they don't seem to be hurting as much as say some of the analysts do.
Okay. So I think then it was a nice root-related meeting, and yes, see you. I hope, Enrico, to hear you next year with full and cooler version of TDataFrame, and yeah, I hope in a few months I will provide you already a tool where you can play and tell me.
Do I understand correctly that this is the last Diana meeting for this year?
Yeah, I think yes.
If so, yeah, Merry Christmas and Happy New Year. And
yeah, exactly.
Talk to you next year.
See you guys.
As I understand, we don't have any planned for early next year as well, so it's time to start planning the next round of talks.
Absolutely. You volunteer? Vince?
Gone.
Okay, have a good one.
Bye.
Goodbye.
Thanks very much for the talks today. Bye-bye.
Bye.
Thanks. Bye.
Bye.